Okay, question 3 is quite tricky. It's not really anything to do with space. It is just, can you do conversions? So we're given our Hubble parameter as 75.0 kilometers per second per megaparsec. Um, this is a unit of distance that we use for very, very large distances. So we need to make conversions to make this work. The easiest thing to do is to get rid of that kilometers and just say this is 75.0 by 10 to the 3. Then we've got it in meters per second per megaparsec. And we're told from the question that to convert from parsecs to light years, you multiply by 3.26, which means then to get from megaparsecs to light years, you multiply by 3.26 by 10 to the 6. However, if you notice, this is not megaparsecs, but per megaparsecs. So therefore, to get from per megaparsecs to per year, or per light year, we would have to divide by 3.26 by 10 to the 6. It's a bit like saying to get from hours into minutes, you multiply by 60. But if you've got something per hour, so say you're doing a certain amount of miles per hour, and you're trying to find out how many you do per minute, you would divide by 60. So when we do that conversion, then it gives us that our Hubble constant is 0.0230 meters per second per light year. Then once again, we're told that to get from light year into meters, you multiply by 9.46 by 10 to the 15. However, therefore, to get from per meter or per light year to per meter, we have to divide by 9.46 by 10 to the 15, which gives us h naught as equaling 2.43 by 10 to the minus 18 meters per second per meter, and the per meter and the meter cancel out. So our answer is 2.43 by 10 to the minus 18. Question 4 is a little bit more straightforward. So it says in the laboratory the wavelengths of the H line and the K line in the emission spectrum of calcium are these values. They're just saying here are some fixed values for lambda, and then they're observed due to redshift to be different. So we're given all the data for the H line, so we'll start off with that and we'll work out our Z parameter, which is just the difference in those wavelengths over the wavelength, which is 19.8 over 396.8, which gives you 4.99 by 10 to the minus 2. No unit because we're dividing a wavelength by a wavelength there. What we can then do is we can work out this for the K line. So we do the same thing. Z equals delta lambda divided by lambda. We put in our values. So the Z parameter will be the same for the H line as the K line. We'll work out our delta lambda, but this time the K line is at 393.4 nanometers, multiplying across. Gives us that the difference in our wavelengths will be 19.6 nanometers, but that's not what the question asks. It asks what would be the wavelength of the red shifted value. So it will be shifted by 19.6 nanometers towards the red side, so it'll get bigger, which gives us 413 nanometers. Part B then looks for the recessional velocity. We just use our other equation. That involves our Z parameter, which is the ratio of the velocities. Taking our value from before, 4.99 by 10 to the minus 2 equals V divided by the speed of light. Works out V as being 1.50 by 10 to the 6 meters per second.